Hello. In this video, we're going to discuss some major ideas from two sections in the online text about one-sided and two-sided limits, and about some of the properties of limits. I'm going to start with an example here of a piecewise function, and below you see the graph of that function, but also I'm using this example to perhaps teach you a little bit about the Desmos graphing tool and how to use it to graph piecewise functions like this. Notice that I've typed the function f of x, and here in the Desmos expression box, I have typed in their syntax, in their language, exactly the same definition of the function that I have typed up here. But notice that it's just written a little differently. So I want the function to essentially output constantly 0 whenever the input x is negative. And so in my symbol definition up here, that's what this line says. F of x outputs 0 if the input x is less than 0. Now Desmos says the same thing in this first set of expressions before the comma there, inside the squiggly braces. It has x less than 0, that tells me the condition if that condition is met by the input variable x. If x is negative, then colon, it will output 0. The second condition says I want my graph to have the straight line x plus 2 whenever the input x is greater than or equal to 0, in other words, positive or 0 itself. And that's exactly what the second half of the expression says after the comma. If this condition is met, x is greater than or equal to 0, colon, then output x plus 2. And there you can see the two parts of the function graphed appropriately. When x is greater than or equal to 0, it's the straight line with slope 1 and y-intercept 2 that you see right there. And when x is negative, it's the constant horizontal flat line y equals 0 that you see over there. And unfortunately, one thing that Desmos does not make clear is that there really deserves to be a hole in the graph right there at the origin 0, 0. That is not a point on the graph, although it may look like it the way it's pictured there. And to make that more striking, notice that my second line of expressions in Desmos says 0, f of 0. I want it to plot the point at x equals 0 with the y-coordinate being the output of the function, and notice how that plots the point 0, 2. So in other words, somewhere deep down Desmos knows that 0, 0 doesn't belong on the graph, but I would argue that it doesn't make that super clear from the picture. So anyway, now you know how to make a piecewise function in Desmos like that, in one line. And I want to use this example to talk about two related limits. Approaching 0 from the left versus from the right. So just a reminder, these notations down here mean imagine what would happen if I let x approach 0, the input values approach 0. What happens to the corresponding outputs? What does the output of the function do? What are the y-coordinates of the points on the graph doing? And the difference is whether I let x approach 0 from the left or from the right. And I've highlighted those two little notations in the corresponding colors to say, as I'm approaching 0 from the left, that means that I'm imagining inputs that are negative but getting very close to 0. So I'm approaching that along the graph on that part of it, the one that's highlighted in blue, and I can see that the y-coordinates of those points are they're constantly 0, so that's why it makes sense that it says the limit is 0. All of the heights are 0 along those points, so it seems like the graph is approaching the height y equals 0 over there. Meanwhile, if I approach x from the 0 from the right, if I make x values that are positive and getting smaller and closer to 0, the corresponding points on the curve, on the graph, are up here, and they're approaching down towards that point that has height 2. And that's why that one-sided limit says this. And now, because those are different, that's why we say that the two-sided limit, as x approaches 0, without specifying left or right, that limit does not exist. And that's what I've summarized down there in the bottom right. Because those two one-sided limits, although they do both exist, because they are different values, that's what makes this two-sided limit not exist. And I've made another note in the bottom left corner there to say that in this particular example, f of 0, the actual output of the function at x equals 0, was 2, but that really could have been any number, and that wouldn't have changed the two one-sided limits or the double-sided limit. It wouldn't change any of the results that I have written on this slide either. If I had made f of 0 equal to 1, for example, and I made this a solid point and that one a hole, well, that wouldn't affect the limit as I approach 0 from the left or from the right, and it wouldn't affect the fact that they're different. They would still be 0 and 2, and so that two-sided limit would still not exist. Here's an example where I don't necessarily have a formula for the function, but we can still read off some information from the graph. The question number 1 up there says, if I approach 8 from the left, so remember that negative means from the left. I like to think of it as negatives are to the left of 0. So when I see 8 minus, I think I'm approaching 8 from just below, to the negative side of 8. So in other words, I'm going to imagine x values that are over here that are getting close to 8. And I see that that part of the curve is going like this, and it's reaching up to a height of, it looks like y equals 0. And so I'm going to say that that limit is 0. I don't care that there's an empty hole there, whether that was filled or not. That would not affect what I see on the graph, which is the y-coordinates are getting close to 0. Meanwhile, from the right, though, if I let x approach 8 from its positive side from the right, I see that the graph is up here, and it seems to be approaching a height of, that looks like 4. So I'm going to make a note of that. Looks like that limit is 4. And I'll quickly note that because those two values are different, therefore the limit as x approaches 8, the so-called double-sided limit, that doesn't exist. And I'm going to very often use this DNE, handy acronym for does not exist, just saves a lot of letters in writing. And I guess I should also mention that it's true, but kind of irrelevant to all of these answers, that f of 8 itself happens to be that point right there, which is at a height of 2. So the fact that that's a different number than the others doesn't affect those results, for the same reasons that I was describing on the previous slide. How about as I approach 5 from the left and the right? So here's x equals 5. So I'm going to imagine the x values approaching from the left. That means I'm down here on this section of the curve, and it looks like they're approaching a height of -7. And while I'm at it, why don't I imagine approaching 5 from the right? I can see the curve heading towards the same place. So for both of those results, I'm going to say that they are -7. And because those two results are the same, that allows me to say this, that the limit as x approaches 5, that double-sided, two-sided limit, that does exist, and it is -7. And then all of that is despite the fact that f of 5 is doing something else. F of 5 outputs this point here at the height of -3. That does not affect, it has no bearing on this fact that as I approach 5 from both sides, the left and the right, the y-coordinates approach -7. This other fact about what f is doing at 5 itself is independent, something else. How about as we approach 0 from the left and the right? Well, as I approach 0 along the x-axis, the corresponding heights on the curve are negative, and then they cross through 0, and then they seem to be shooting way up there. And this is something that's a little bit of a preview of stuff we'll get into in later sections, but I think you could be comfortable enough right now to agree with me that it's fair to say that that limit is positive infinity. It seems like the y-coordinates, the heights of those points, are just going to get taller and taller and go higher up the y-axis. So we're going to say that that limit is positive infinity. And so I just want to be a little careful and say that, technically speaking, that limit doesn't exist, because it's not approaching a specific number, like 8 or 1,027,000 or whatever it is. It's not approaching a specific value, so I don't really want you to get the impression that this limit exists and that it is infinity, although it kind of is in some way. But it's more likely that you'll read about this in other sources and say that this limit doesn't exist, but we can give a very specific reason for why it doesn't exist. It's because it's not approaching a specific number by getting bigger and bigger. But meanwhile, from the right, it's doing something quite different. As I approach x equals 0 from the right, from the positive side, it seems like the y-coordinates, the heights of those points, are approaching that value there, which is -3. And so here's another case where I could say that the limit as x approaches 0, the double-sided limit, that doesn't exist. But it's kind of a different reason from the other examples we've seen so far, where the two one-sided limits both existed but approached different numbers. In this case, we have a one-sided limit that does exist, the -3, and we have another one-sided limit on the other side that just doesn't exist. So it doesn't matter whether this was -3 or anything. The fact that one of the one-sided limits was infinite, that it didn't exist, that immediately allows me to say that the two-sided limit doesn't exist. It doesn't have a valid value, a meaning either. For -7, I'm going to just skip ahead to the final question, number 8, because it's much easier to see. I hope you'll agree that as I approach -7 from the right, it seems like the height of those points is approaching that value down there at, again, -3. So I'm going to write that down. And again, it is true that f of -7 is -3, although that's independent of what the limit's doing. And I also suppose back here I should make a note that f of 0 itself, by the way, I don't see a point defined at x equals 0. So I'm going to say that doesn't exist either. There's a hole there at x equals 0, and there's no point somewhere on the y-axis like this. This one is approaching it asymptotically upwards. So in fact, there's no point on the graph where x equals 0, so that's why I say that f of 0 doesn't exist. But again, that fact has no bearing on any of the limits we're talking about. And okay, so let's jump back to the -7 situation. Over here, I'm approaching -3. There is a solid hole there. F of -7 is -3. But neither of those affect what's happening as I approach -7 from the right. And I can see the curve do something kind of wild, and I hope you remember or recognize this from our online notes and some examples in other videos and homework problems. This is meant to be one of those wildly oscillating functions, like the cosine of pi over t example that you saw in the online notes. This example, this limit, does not exist because it's failing to approach a specific number. It's wildly oscillating up and down between whatever those two y-coordinates are up there, and I tried to draw something that's similar to that. And there I've written down that limit that we saw in the online notes and in a prior video that hopefully this graph up there reminds you of. Okay, so now we've talked about one-sided and two-sided limits. Here is a slide that has a list of some common properties of limits. And as I'll describe as we go through this and in a summary slide at the end of this video, none of these are particularly surprising. All of these are pretty much what you'd expect. So, and I kind of write that in the theorem box. Assuming that I have two functions, f and g, and they approach particular limits. So in other words, if I have, if I have the function f and it's approaching some limit L as the input gets close to a, then I have another function that's approaching some other value like m, then various combinations of the functions, like adding them together or multiplying them together or dividing them, all of those will cause the resulting limit to be pretty much what you'd expect. If I add the two functions together, that will amount to adding their limits. If I multiply the two functions, that will amount to multiplying their limits. And if I divide, that's fine as long as I'm not dividing by 0, as long as that second limit is not 0. So that's what I meant by a lot of these will make the limit be pretty much what you expect. Adding, subtracting will make the limit be adding and subtracting. But I also want to make sure you recognize that there's a reason all of these things are what you'd expect them to be, and it's, I hope, based on some knowledge you have about functions and their graphs and combinations of functions. So for example, let's look at property number 3, which says if you take a function and you know its limit exists, and I scale, I multiply the function by a specific constant number, c, then that will cause the outputting limit to be that multiple as well. And so that really comes from the fact that if I have the graph of some function f, like this, I've sketched out cartoonishly down here, then what does it mean if I take 2 times that function? Well, that's exactly like stretching out the graph to be twice as tall. If I take any point on the graph and I look at how high its y-coordinate is and I make that twice as big, that will give me the y-coordinate on the doubled function. Same idea over here. And so, of course, if I'm approaching from the left and the right, and it's approaching that value, and I look at 2 times the function, it's going to do exactly twice as the original value. It's what you'd expect. But that's based on something we know about graphs of functions. This isn't really saying anything new. It's telling us something about limits, which we're learning about right now. But I hope you can see that it's predicated upon something you already know about graphs and transformations of functions. And very quickly, just in passing, I'll note that all the other properties come from similar things you know about functions already. Like if I have the graph of 2 functions, f and g, then the graph of their sum is essentially like stacking the graphs one on top of the other. So if I know the height of the f function here, and I know the height of the g function, then adding those 2 heights together is how tall the corresponding point is up there on the summed graph. And that's why you'd see that come out like that too. So pretty much everything you'd expect to be true about these limits is. And that's based on things we know about graphs of functions. So let's start applying some of these properties. But before we do that, I just want to actually be really careful about a subtle logical point. So let me jump back to the statement of this theorem here. It says that assuming those limits exist, assuming that f approaches L and g approaches M, then a whole bunch of things are true. And I want to draw your attention to the fact that I cannot reverse the order of those things. I can't start from the conclusion, and hope to get back to the assumptions. In other words, I can't turn the logic around. It does not say that I can reverse that. So just as a quick example that I'll demonstrate on this slide, let's say I have 2 functions in mind, f and g. And I tell you that it is true that as x approaches 0, their sum, f plus g, that does approach 0. This limit does exist. So let's say I'm telling you that this is a true fact about my functions f and g. Does that tell you anything? Can you say anything with certainty about the limits of my individual functions f and g? And by with certainty, I mean, can you be sure? Or are there still unknown possibilities that you would have to account for? So, for example, it might very well be true that if my example functions f and g that I had in mind, suppose I had in mind f is the constant function 2, g is the constant function negative 2, then certainly these 2 facts about f and g, those limits, are what they are as stated right there. And it would also be true that their sum is the constant 0 function, so this would be true about them. So I guess sometimes it might very well be true that it's what you almost half expect, that one of them approaches some number and then one of them approaches the negative of that number. So when I apply the limit properties and I say 2 plus negative 2, I get 0 as the result. And that's fine, that could happen. But I want to show you an example to say that it's also possible that these 2 individual limits, f and g, they just don't exist. And yet still their sum approaches 0. So I'm going to give you a minute to pause the video and think about that on your own, see if you can come up with an example. So have you come up with anything? Are you able to find 2 functions f and g such that these limits don't exist, and yet this limit still is 0? Here's something that I came up with, and I'm not saying you necessarily should have come up with exactly this example, or even with any example. I just wanted to get you thinking about it. And this also dips a little bit into some limits dealing with infinity, kind of like I previewed in the example back here on the graph as I approach 0 from the left. We talked about how that's infinite. Very similarly, I could make up the function f being 1 over x squared, and its graph looks something like this. It has these very steep curves that approach infinity on 0. As I approach 0 from either side, the curves go up to infinity. There's a vertical asymptote at x equals 0. And if I make g of x the opposite of that, then obviously it has the same shape but flipped across the x-axis to be a mirror image on the other side. And then the sum function f plus g really still is the constant 0. although I guess I should be a little careful there to not erase everything, but also to say there's a hole in that function at 0. So I'll say except at x equals 0, because the two individual functions f and g are undefined. There I would have division by 0. And yet still the limits are all what you'd expect. The sum function approaches 0 as the input x approaches 0, and yet the two individual limits of f and g don't exist as I approach 0. So all of this is just to say be very careful and also, appreciate the fact that this theorem is true. It seems super obvious, but it tells you that what you expect from your intuition is correct, and that's a really nice thing to have in mathematics. But it's also essential to understand when that intuition breaks down, or when that logic breaks down. Okay, so now let's apply these properties to a couple of examples. Here I have x approaching -2, and then here's my function on the inside. It's root 4x squared plus 9, and I'm going to think about reading this from the inside out, from the order of operations perspective. As x approaches -2, isn't it true that x squared will approach 4? And I'm using these arrows here to mean approach. So in symbols, what I just wrote down is what I wrote in green there in words, which says as x approaches -2, x squared approaches 4. And what I'm using there is the property number 6 down there. It says if I have a function f that's approaching a limit L and I raise that function to some exponent n, in our case, in my example, n is 2, I'm squaring the function, x, then the corresponding limit will be the limit L to that power n. And I say for any n that makes L to the n make sense, and by that I mean make sure we're not taking the square root of a negative or I'm dividing by 0 or anything invalid like that. And here in this case we aren't doing that. We have -2 squared, that exists, that's 4, and so that's why this makes sense. And then what's the next kind of order of operation? That x squared is multiplied by 4. So as x approaches -2, I can therefore say that 4x squared will approach 4 times 4, or 16. And then as x approaches -2, it will also be true that I can add 9 to that, and that will approach 25. So in these two steps, I'm applying the multiplication property and the adding property, or in other words, back too far. I'm applying property number 4 there, and I'm applying property number 1, I guess, with the function g being just a constant 9. Now I'm not going to make you cite these properties by number or name or anything like that, but I'm just pointing them out here to say we're relying on our intuition, but we also have that theorem, that list of facts that backs up our intuition. So I do think it's helpful, at least in this moment, for me to point to those properties as we apply them, but I'm not going to make you do anything so formal as, cite the properties in order or anything like that. The last step I'm about to do is take the square root. And so as x approaches -2, isn't it true that the root I could also express as a 1/2 power? This is something that we're going to be doing a lot in our course, so if you haven't seen this before or need a reminder, just remember that I can always write roots as rational exponents, fractional exponents like this. And that means this whole limit is going to be 5. And here now I'm applying the same property that I did up here that said I could square both sides. It says I can also square root both sides as long as it makes sense. And here it does matter that 25 is positive. I'm not taking the square root of a negative. So that's an example where I had a specific function. Here's an example where maybe I don't know anything else about the functions except what their limits are. And so let's say I know that as x approaches 3, f of x approaches 2. So that's kind of like the L in the theorem. And as x approaches 3, g of x approaches -2. That's kind of like the M in the theorem statement. And then what's going to happen as x approaches 3 from the right of this fraction? Well, I'm probably going to apply those properties that say I can do 4 times the function, I can cube a function, I can double it. I'm going to apply all those properties. But I also carefully crafted this question to make you think about how both of these say as x approaches 3, but my question is really about as x approaches 3 from the right. And are those different? Pause the video just for a second and think about that. I hope you realize that telling you that as x approaches 3, f approaches 2 is really telling you two things together. It says that as I approach 3 from the right, f approaches 2, and as I approach 3 from the left, f of x also approaches 2. So encoded in that one notation there, in that one set of symbols, are two facts. And therefore, everything I know about x approaching 3 I can apply to x approaching 3 from the right, because it's just one half of those facts. So now I essentially get to apply the properties that say, well, f's approaching 2, so the top is going to approach, I should get 2 there, and then g is approaching -2, so I can plug that in there. And the bottom, f is approaching 2, so I can cube that. And let's see, that's going to be 2 minus, so plus 8. 2 times 2 is 4, times 2 is 8, times another 2 is 16. So I get 10 over 16, or 5/8. And that would be a perfectly valid answer. So that one feels a little, to me, too much like just kind of plugging and chugging. There's not a lot of conceptual thinking behind that. So I just want to close this video with a short little discussion about these limit properties and the concepts behind them. And I'll say what I said before, none of those properties is particularly surprising. Oh, you add two functions and it's like adding their limits? Big whoop-de-doo, shocker. But I don't think that means that those properties are pointless or not useful or really uninteresting at all. They are super useful and they're fascinating. But I do think that examples asking you to apply the limit properties and cite them like that are rather contrived. Like I'm not going to make you write out I use property 2 here and then I use property 5 here, blah, blah, blah. I don't think that's particularly enlightening or helpful for learning. But I do hope you draw some lessons from this. One is that mathematics involves building up a body of factual information and then applying those facts to do new things and extend the body of knowledge a little further, and then to take that set of facts and extend the body a little further. So think of this as you're learning about calculus, you're learning about limits right now. Absorb those properties as part of your body of known facts and use them to do and learn new interesting things. And as part of that, I think it's helpful to recognize when we're doing something new versus when we're doing something that is known. Like when I'm, quote-unquote, solving this problem, I'm kind of doing something new in the sense that I'm evaluating a limit, and we're learning how to do that right now in this unit. But I'm also applying known things, which are essentially that these nice combinations of functions, squaring something, multiplying by 4, adding 9, taking a square root, those all play nicely with limits. They all behave well, and they match up with our intuition. And so I think it's helpful to recognize that that's happening, and then to recognize that there are other situations where the intuitions don't really play out well, like this example I was describing over here. Another thing is that taken together as a giant list, all of those properties of limits collectively say things that we pretty much really already know about functions and their graphs, but they're stated in new language. They're stated in facts about limits. And I think it would really help you to think about how you already kind of know all those things because of what you know about graphs of functions. But I'll also say that all of those facts can be proven in more detail. I know it feels super obvious to say, oh, the sum of the functions is the sum of the limits. Like, what more could you want me to say? Well, all of those facts can be broken down into more fine detail and proven with formal logical thinking. And so in our online text, we may dip into the section about the formal definition of a limit, which you can use to show that those properties are true. And you might certainly do something like that in a course on real analysis. And so 2 quick points about that. First, being able to prove something like those limit properties using the formal definition of a limit, I think it's really important to point out that there's something beautiful and powerful happening there. Because notice in this theorem, this list of properties, it says, assume that I have a function f approaching L and a function g approaching M, and that's really it. Those are very bare bones assumptions. I'm not telling you anything about the function f or g, whether it's a smooth continuous curve or something crazy like the cosine of pi over t example we've seen. You don't know anything else about these functions, merely these two very little pieces of information that those limits exist. But knowing just those two things, you can say with certainty that this fact will have to be true, no matter what those functions f and g are like, no matter how complicated they are. And that's really powerful. I think it behooves you to try to appreciate that a little bit, that this is true without me telling you or needing to know anything more about the functions. And so that's something that's going on behind the scenes there, where you can prove a fact for all possible examples all at once, and not just for specific examples like the practice problems we were just doing. Those are interesting and helpful for learning, but I think the really cool and beautiful stuff is going into the behind the scenes work of that theorem itself. It's showing something about an infinitude of possible examples all at once. And so we won't really get into that in our course, but where you will do something like that is in a course on real analysis. And I'm going to give the analogy that my professor who taught me real analysis in college told me. I don't think he made this up either. I'm just passing it along the generations. But it says that in terms of a kind of SAT-style analogy here, calculus is to driver's ed, as real analysis is to becoming an auto mechanic. So in calculus, what you're doing now is we teach you how to drive the car around, how you get from point A to point B, how you press the gas appropriately, when to stop at a stop sign. You know, you can get around town, you can drive a car, you can do stuff. And that's really super helpful, and a lot of people can and should learn how to do that. But I don't know about you, but I went through driver's ed and got a license, and I still drive a car around, but if I'm being totally frank, I have no clue how a car works. I don't know how the engine works. If my car breaks down, I am completely clueless. And so in real analysis, we get into the behind-the-scenes stuff. We get to lift the hood of the calculus car and peek in at the engine and talk about how everything works. What does the gasoline do? What does the engine do? What is that little part over there? What's something that we do in a car, like hit the brakes? When I do that, can we look under the hood and see what's happening there? That's what real analysis is all about. It's teaching you how the calculus car operates. It's teaching you to become an auto mechanic so that you can modify the car to do your own stuff and do new and cool things and not just drive around like everybody else. So if you're interested at all in learning more about that, feel free to talk to me. But I hope this kind of whets your appetite for some of more advanced mathematics. All right, that's all for now. See you next time.